All right, this laser represents the sun. I got it coming in from a distance. Right here, lined up dead at the equator during the analemma. Come see this. Okay, the sun's dead on the equator, and that represents the sun. So you spin the sun, and there it is. Well, it goes that way. There it is. Okay. Now there's the analemma, and here's how the season goes. So, see, so right there in the northern hemisphere, summer, the sun is at the top of the analemma. Okay, and as you go, it goes back down. Okay, and this represents the winter. The southern hemisphere's winter. Okay, the sun's down there. Now, it's claimed in Australia, the sun comes in from the south. Okay, so this is the angle we see the sun. So you could point any old way you want on Google Earth or whatever. This is what we see in the sky. This right here. So as Australia comes around, I exaggerated the lines of latitude. Okay, this is the middle of Australia. This is 30 degrees. See, there's the laser right there. Okay, and more proof. Okay, so that they'd start seeing the sun, I guess, when it's about right here, right, actually by the analemmas, when it, or about right, somewhere, let's say the sun's about right there, that's where they're going to see the sun when Australia starts poking its head up. Okay, so right there, that's the analemma, that's Australia. It comes in from the east, they could say whatever, but if it's supposed to be the same as in the north as it is the south, I happen to live at 30 degrees north. Okay, now you could, like I said, you go to Google Earth and show which way east points. It doesn't matter. If it was coming in from the south down here, then the sun would be coming in from the north up here. And it does not. It comes in from the east, just like it shows on the damn analemma. Another little trick they like to play. Another little trick they like to play is like on computer programs, they take and they tilt. They bring the sun in from 23.4 degrees. Okay, so it'd be coming from down there. Okay, but this is where that fails. Okay, so yeah, that would work out as the same angle in one spot. But look, you could do that. But then you have to rotate the sun around it. If you're coming in at that angle, you have to rotate the sun. Else the sun would always be right on the equator. Common sense, folks. Common sense. That don't work. That's the little trick they like to play on their computers. But if you're going to angle the sun down there at 23.4 degrees to say that the sun comes from the south during the winter for Australia, then you'd have to rotate the sun at 23.4, and then it'd be an elliptical orbit like that. So either way, it doesn't work, folks. Yeah, man. What I'm showing here, everybody's seen, it's the distance to the sun and its extremes, the closest we get to the sun and the farthest away we get from the sun, and it adds up to a few million miles, or 3.4%. Okay, now that 3.4%, excuse me, is supposed to cover, it's supposed to be the cause of, or the elliptical orbit of the Earth. Okay, that difference in distance is the cause of the elliptical orbit. That's not much of an ellipse, but we'll give them that. It's also supposed to be the cause of the bigger loop in the south, or the lower part of the analemma, is the variation in orbit. Okay, now looking at the analemma, it's way bigger than 3.4%, that loop. So that doesn't work one bit. Also, I looked up the lunar analemma, which is over 1 month. The sun is over 1 year. The position of the sun in the sky at the same time every day for a year. The lunar is over 1 month, okay? And they're identical, okay? But you look up the distances during apogee and perigee of the moon, and they vary by 13%, okay? So if 3.4% causes such a big loop at the bottom of the analemma, then 13% would be huge, but it's not. So I'm going to go with Occam's razor on this one. On a flat plane, the analemmas work better, period. Okay, they're explained by the bigger loop the further the sun goes out, and the seasons are also explained better No big long explanation about angles of the sun and how much land is there and how much energy is being absorbed. Just closer, sun closer, summer. Sun further away, winter. Simple shit. The page coming up says the ultraviolet catastrophe. And originally I posted that to just show the spectrum of colors and how the more energy, the way the colors change, the lowest energy being red and the highest being blue. Well, then it goes higher. You combine them all. Higher than blue is white, and then you enter the ultraviolet, which is not visible to humans without optical assistance filters. But and then X-ray, and then gamma. But it's relevant. I'm trying to put together a model, which I obviously need help on, but I'm trying to go by what we see in reality. Okay, and what we see in reality is light slowing down, okay, through a medium, and it's acknowledged, but it hasn't been associated with everything in reality, in my opinion. Like distance should be a factor, okay, and a lot of these things are known today as common knowledge or general science knowledge that weren't factored in to the model hundreds of years ago, okay? And the reason they call that the ultraviolet catastrophe is because they made the old law, the old equation, and when it got to the ultraviolet spectrum, it broke down. Instead of keeping going up, it went down, like leveled out and went down. And they explained this away by, first off, Planck just observed reality and wrote a formula, or hit Planck law, to match reality, just guessing at it, and admittedly guessed at it, which is what I think they did with a lot of laws, but I'll talk more later about that. It says here, if the speed of light were slow enough, Newtonian physics could become a poor approximation of reality. The fastest that we could go would be slower. The speed of other massless particles would likely also be the slower speed of light, and special relativity would have significant effects at slower speeds, or the light would just change color and not go as far, like what happens in reality. All that other shit, or it just slows down, maybe changes color.
Is I stuck this black plate in here, this metal plate, and then I heated that up, and that is what we saw escaping here. So the only reason we could see anything coming out of it is because it was being heated from inside, and that light was able to escape outward. It turns out that no matter what your black body is made out of, if you heat it up, it will always glow at the same temperatures. Now, I wasn't able to get mine to a very high temperature. I probably got it to around 700 degrees Celsius. But if I could get it to a higher temperature, then it wouldn't just glow bright red anymore, but it would actually start to glow yellow and orange. And if I heat it up even more to around 1300 degrees Celsius, then it would become yellowish white. And the reason it starts glowing white at 1300 degrees Celsius is because you have red light, but then you added the medium range light, the mid-frequency light, and then you added the high-frequency light, like blue light, in there. So when you have the low, medium, and high-frequency light all together, that makes white light. You basically have the entire visible spectrum being emitted, and so it looks white.
Now this lady is explaining how they slowed down light using extreme cold temperatures in a Bose-Einstein condensate, which is probably right there by absolute zero, if there is such a thing. But if you pay attention, you'll see where they clock the speed of light in her experiment, and it looks like it goes down about as low as 9 meters per second, and it starts trickling up, 10, 15, 20, 30, 40, 50 miles per second. And the variable in that experiment apparently is temperature. So unless they're just hitting a temperature and the light slamming on brakes, it appears to be gradiating up as more heat as they lose that extreme cold. I don't know how long they can maintain it, but I would imagine the more heat added to the system, the faster the light is going to go until it reaches maximum speed or propagation, whatever you want to call it. But what color does light turn when you slow it down? If it's yellow, like I showed a video before with the yellow diodes turn into orange and red. And so I'm comparing that to an eclipse, the blood moon, and sunsets and sunrises when the sun's at its farthest distance, how the atmosphere appears red and the moon appears red during the blood moon.
Right down to, to a human level. I thought that was just absolutely fascinating.
Lena Howe created a cigar-shaped Bose-Einstein condensate to carry out her experiment. She fired a light pulse into the cloud. The speed of light is around 186,000 miles per second, but when the pulse hits the condensate, it slows down to the speed of a bicycle.
So light pulse might start.
So we got to think of the implications of these things, and it's fun too, if nothing else, and see what we can come up with. So the reason I showed these videos is because the sun's light is traveling a long way before it sets, okay, or before lunar eclipses, okay, and when the sun is farthest away before it sets, you see it turning red, okay, and you see the atmosphere turning red, exactly what these videos were, and what science dictates. It's just more coincidence if you want to put it one way, but to me it's accepting reality and modeling it out. I don't think it has to do with the refraction the way they say it does. It's not tied in properly. You see the eclipse, okay, you see the shadow coming in from the top down. That can't be explained on a globe model. And the lunar eclipse basically always comes from the top down that I've seen. And if it's the Earth making the shadow, that's just not the way it would happen. Let's accept reality and let's put our heads together and get it right, okay? Like I was talking about the ultraviolet catastrophe earlier. Like they had the math wrong, okay? And therefore, it was completely wrong. This wasn't an instance. This is an instance where they admitted it, but they didn't update the math. They completely changed it. And they basically did it by saying it's a different energy. It's a different energy, okay? So just because you're adding, you're not adding more energy, it's different. But it's that's how they explain it, to my understanding, in the quantum realm. But they admitted that one. Maybe they got caught. But look at these cycles of the eclipses. They repeat every 18 years. This is known. This is mapped out. No, not on a globe. It's not the globe model that predicts these lunar eclipses. I love it when they ask me about lunar eclipses. They're basically just committing suicide in the debate. But you could look at these. It's on Wikipedia. Anybody could find them. They repeat, they skip days sometimes only by hours, okay? They repeat in cycles every 18 years. And it's, about two a year. Twice a year, the sun gets far enough away from the moon where it shadows out.